Hello, I'm Junggu Lee from KAIS. Today I'll present how we could turn a large collaborative robot into a practical haptic display by removing friction in an energy-based, model-free way. This paper is originally submitted to a transaction on mechatronics. Collaborative robots are attractive for haptics. However, joint friction reduces transparency and makes interaction feel heavy. Conventional friction compensators typically require system ID and tuning. Some model-free online methods exist, but they often underperform. Our idea is simple. We estimate friction from energy cycles, which does not require any model information, and we compensate friction online and also guarantee passivity with additional controller. Here is the setting. A human operator interacts with a robot joint that has internal friction. The human-robot energy exchange can be computed by integrating input power over time. Assuming human is giving a sinusoidal movement, you obtain an energy profile like the figure on the right. And what's comprising this energy? The energy injected by the human is partly stored as a robot's kinetic energy and partly dissipated by joint friction. We care about dissipated part. The question is, how can we isolate it? The idea is simple. When the joint velocity becomes zero, the kinetic energy also becomes zero. Therefore, at those instances, the input energy over the cycle equals the frictional dissipation in the cycle. We define an energy cycle as the interval between two zero velocity instances. This relation makes friction observable without a model. Based on the energy cycle, we obtain the amount of energy dissipated by friction. From that, we estimate the friction parameters for the preceding cycle and apply the corresponding compensation torque to the controller. As shown in the last figure, friction is updated after each cycle and immediately used for compensation. The friction compensator is active component. Therefore, it has a risk of overcompensation and system may become unstable. We use the time domain passivity approach to keep the interaction passive and stable. We validated the proposed method on a Franca Emica Panda in a single Dove interaction task. Without compensation, the net input energy keeps increasing during interaction, and the torque velocity plot shows clear hysteresis. With the proposed compensation, after the first few cycles to estimate the friction, the energy no longer rises. The torque velocity ellipsoid becomes thinner without hysteresis, and the required torque level drops, which means the device feels lighter. We compared the proposed approach with other approaches. Ours is the only method that consistently holds the energy flat. The others reduce the slope, but it keeps increasing. This means that our approach is the only method that can effectively compensate the inherent friction on the joint. In the torque velocity plot, our method exhibits the lowest torque levels and the smallest hysteresis as well. This short clip contrasts the two conditions. Before compensation, it is hard to move a single joint with just a name card. With our compensation, the joint moves easily, showing how much lighter the human-robot interaction becomes. To summarize, we proposed a model-free, energy-based online friction compensation method. The core is utilizing the energy cycle to estimate and compensate the internal friction. Also, we ensure system passivity using TDPA. Furthermore, we validated and compared the proposed method with a commercial robot arm. It shows no energy dissipation, a slimmer torque velocity profile, and it outperforms representative baselines. Thank you for your attention.